Hey, everybody, welcome tonight. It looks like we've got pretty much everybody. Maybe a few will trickle in, but I'm going to go ahead and hand over the controls to Dr. Tom Smiley. Welcome to our first 2023 bi-monthly training of the year. We appreciate you being with us tonight. Dr. Tom Smiley. He is a lead researcher at Bartlett Tree Labs, and Bartlett speakers tend to be our biggest attended speaking event. So thank you so much for being there.
Okay, thank you, Brittany, and I will go ahead and start my presentation here. I am going to be talking about lightning protection today and about treating lightning damage. Start out with a video, and I'm hoping the sound will work on this one. This is a camp up in Canada where the tree gets struck, white pine. And you can see the force of the lightning totally damaging, totally destroying this tree. Going to run it again for you there. And you can see the pieces that are coming down and being blown all over that camp. So the power of lightning is quite remarkable. Here's an animation showing you what is actually going on, a little bit slower speed. So we have the cloud going over the top. It is charged, and we have charges shadowing that cloud in the earth. And as the cloud with, in this case, the negative charges goes over the top, it draws what are called streamers out of the tall objects, whether they be the house or a tree, doesn't really matter. And the cloud then sends down what's called a stepped leader, and it connects with one of the streamers. And once that connection is made, that there is an exchange of electrical current, typically 3 times in the United States. So typically down, up, down, but it can be in other orders, and the charges aren't all negative to positive. Sometimes it goes from positive to negative, but you get the idea of what's going on there. Now, with lightning strike density, this is a map of the US, and it shows that we have the most lightning in the country in Florida, and then it gets less and less as we go north. In Georgia, we have some areas of really severe lightning down in the southeast corner of the state, and less as we get up north toward Atlanta, but still a lot of lightning across all of Georgia, with many other parts of the country. Well, why do we protect trees? There are a number of reasons. The first one's pretty obvious. We want to protect that tree from lightning damage. Number 2 is we like to be able to draw lightning away from other trees and structures. So we can never sell the fact that a lightning protection system in a tree may draw lightning away from a house, but indeed it might to some degree. There are limits to this. We've been trying to research what those limits are, and we have a bit of an idea about that. We'll talk about that later. And then lastly, there are 2 parts of lightning that can injure or kill people and other animals, and they are called step voltage and side flash. And I'll show you what that means and show you how we can protect it. So this is slide flash. So the lightning's coming down, hitting a tree, and then jumping over, in this case, to an unsuspecting golfer. If we were to have a lightning protection system in that tree, the results would be a little bit different. The lightning would be conducted safely to ground and not side flash over. So that's a really good one to be able to protect against. The other one is step voltage. It's similar in some ways, but in this case, the lightning is coming down, going through the tree, and it spreads out over the soil surface. As it spreads across the surface, there is a difference in electrical potential. And if, in this case, the dog has its paws, 2 paws closer to the tree, 2 further away from the tree, and because of that distance difference, there's a voltage difference, and lightning can go up through a dog or a person. We see it more in wildlife, though, actually in cows and horses, because their feet are more widely spread. So it can go up 1 paw or leg and then down the other. And again, with the lightning protection system in the tree, we try to get that lightning deeper into the ground so it's not just on the surface. Let me run this one a second time, and just so you can see, we're illustrating this explosion, and that happens sometimes when the lightning goes into the ground rod below ground. We have an explosion that occurs both as the lightning attaches to the lightning protection system at the top, and often there's an explosion in the soil as the lightning leaves the system. Oops. Okay, didn't mean to rerun that one. Okay, so here's an actual photograph of the streamers being produced. So they got very lucky with this photograph that it was just after that connection and exchange of current. But you can see these streamers coming from all of the tall objects here. So it's coming from the tree. There were multiple streamers from the tree. One connected, this one did not, that we can see. And then there's an antenna off to the left and another tree to the left and a tree to the right. They all produce streamers because of that differential in charge between the cloud and the soil. Now, they've measured the length of these streamers, and typically they end up being between about 30 and 300 feet long, which gives us an idea for what the protected zone is around the tree. So I'm looking at it here as a cone over the top with a radius of 30 to 300 feet, and then we would have that same sort of cone going on down to the ground. That's where we'll be drawing the lightning into the tree. So, when we talk about tree lightning protection, we're actually not keeping that lightning off the tree. We're actually inviting that lightning to hit our tree, but then we can conduct the lightning safely to ground. So here are some of the basics of a tree lightning protection system. We have an air terminal at the top, and this is where we try to have that lightning connect to the system in the tree. And there are ways of doing that that are more effective than other ways. Then we have a conductor. This is basically a woven copper cable that runs from the air terminal down the tree to the ground rod. We have fasteners along the way, unique fasteners for attaching it to the trunk or branches, and then some fasteners to connect that conductor to the ground rod. Some other factors on here are we're showing the distance between the fasteners is 3 to 6 feet, and we're illustrating the depth of the ground rod and the distance from the trunk. And we'll come back and talk about all those details as we go along. So basics of lightning protection: when we're setting up a system, we select where we want the ground rod, and we often have to start here in urban areas. We don't want it going toward a house. We'd rather have it going away from the house. But we have to consider where there is an underground electrical connection or where there are water pipes or gas lines, and run away from all of those infrastructure features. Then we would select the air terminal. We'll come back to that in just a minute, and a route for the conductor down the tree. We pull the conductor to the top of the tree, along that route, fasten it to the tree and to any support systems that we have in the tree. So if we have a steel cable in that tree, we would want to connect that to the lightning protection system. The reason for that is that there may be that side flash occurring. So it may actually hit the steel cable first and then jump over to the lightning system. And if it does, we want to control that flash by connecting the steel cable to the lightning conductor. And then we will trench for the ground conductor, dig a pit for the ground rod and connect those. We'll drive the ground rod and connect the conductor. We'll show you some more details on that as we go along. So in most trees with a single dominant leader, we can just hook up our air terminal at the top of that leader as high up as it's practical to get, meaning 2 or 3 inch diameter wood. We don't want you up there in 1 inch wood whipping around to connect the to connect the air terminal. You just need to be up in relatively small wood. 2 or 3 inch diameter stem is where we would typically go. But if we have a wide spreading tree, we do have some guidelines from the ANSI A300 standard, and that is that we would like all parts of the tree to be within 35 feet of that air terminal. So in this case, we have a codominant stem tree, and instead of putting it up in this stem, because if we did, we would be further than 35 feet to the other stem. So we're going to split this and have two air terminals and two conductors, all of which are within 35 feet of all of the branch tips. So we don't really have to worry about this in trees unless they're more than 70 feet in diameter of crowns. So our preferred air terminal is now a blunt tip. It used to be a sharp point. If you've been around the industry for a while, those were called Franklin tips because they were invented by Benjamin Franklin. But what research has shown in the last decade or two is that these blunt tips tend to be more attractive to lightning. So we would like to attract our lightning to the system as high up as possible. And to do that, we use these blunt tips. If you've been to the Bartlett Tree Research Laboratory in Charlotte, you may have seen some of our lightning protection systems in place in trees there. We have about 100 systems. And with those systems, we do research on things like this, on different types of tips. And we have confirmed other researchers' findings that the blunt tips are actually more likely to get struck, and the lightning is more likely to strike the tip. With the sharp points, the Franklin points, we're actually just as likely to have the conductor struck further down the tree. But we would like to have that strike further up. We know that there can be an explosion at this point where it connects to the lightning conductor. And if that explosion does occur, we would like to minimize the damage by having that tip and the explosion up as high as possible in the tree. And that's how we achieve it, is with a blunt tip. Well, after we choose that location and install it with our first dry fastener, we then install the dry fasteners every 3 to 6 feet down the trunk. So if it's a straight run, you can space that out to 6 feet. If there's a curve in the trunk or branch, we would space those conductors more closely together. On some real sharp bends, we get even closer than that. We may have to go with 18 inches or 2 feet just to keep the conductor off of the trunk, and that's just fine. The 3 to 6 is sort of a guideline for spacing. It is okay to space them closer than that, but in general, we would not want to go beyond 6 feet beyond conductor because that conductor may move around a little bit too much. So again, we want this to be a nice smooth run down the trunk. And one pro tip here is on a branch like this where a climber may be walking in the future, we would rather have that conductor off on the side of the branch so that the climber doesn't have to walk on it. And then once we get back in the vertical orientation, it doesn't really matter where that conductor is fastened. Well, when we get down to the ground, we want to have our trench dug. This needs to be at least 8 inches deep, and it needs to be at least 10 inches long. 10 feet long. From the trunk to the ground rod, we also consider the trunk diameter. So if we're more than about 3 feet in diameter in the trunk, we would use this distance to 3 times that trunk diameter before we get to the ground rod. So going back for an example, if we had a 48-inch tree, 3 times 4 feet is 12 feet, we would want to put the ground rod at least 12 feet from the face of the trunk. So generally a lot shorter distances than we used to dig in the old days. And if we have large roots, especially near the trunk, we do want to take care not to damage those roots. So we can dig underneath those roots and do some little tunneling if we need to. The greater the separation from the roots to the conductor, of course, the better. That said, we have gone back and dug up a number of tree roots close to conductors, and in general, we don't really see damage close to the trunk. I'll show you in just a minute where we do see damage underground, but it's typically not in the roots shown here in this photo. And of course, if there's any chance that we have underground utilities, we do want that searched out before we do the installation so that we can change the course of the ground rod trench if need be to avoid the underground utilities. So again, one way to simplify the installation of the ground rod is pre-drilling our ground rod hole. So you can take an earth auger on a gas or electric powered drill and drill it out. That gives you 2 or maybe 3 feet of distance that you can put the ground rod into the soil before you start driving it in. That makes it so you don't have to stand on a ladder while you're installing the ground rod. Makes it a safer operation for our crews. And then once we get that started, we can use a ground rod driver. This is a little bit of an older version of a ground rod driver. It's got that heavy steel cylinder on it. This one does not have hand-hold areas on it. So there were some problems with this type of ground rod driver that if you lifted too far up, it has happened a few times where people will bring their hands down outside of that tube where the ground rod should be, and it ends up in your hand. And that is not a very good situation at all. So they put handholds on these so that that is far less likely to happen. If you have a demolition hammer in stock, demolition hammer makes a great driving tool. If it's got the drill as well as hammering capabilities, you can drill with it and drive it in. And if you're doing multiple ground rods on a job, I would highly recommend renting one if you don't own a demolition hammer. There is a special bit that you need to get that is made for ground rods, but that is not particularly hard to come by. Well, where do we put these ground rods? We've already talked about the minimum of 10 feet from the trunk. And if we're in Piedmont sort of soils, clay loam soils, we can just stop there. But if we're down on the coastal areas, or if you happen to have a sandy or gravelly site, then the standard calls for 2 ground rods. Ground rods are typically 8 feet long, and there are a couple of ways to do this. One illustrated with the photo on the lower left here is we can drive one ground rod here. We can use what's called a compression fitting right in here, which is a fitting, basically a short section of pipe that is tapered on both sides. And then we drive the second ground rod right on top of that. And then we basically produce a 16-foot ground rod. And that should give you a really good ground in most soils. But if you have too many rocks in your area, it can be hard to drive 16 feet of ground rod. So there are some other options. One is illustrated up on top here, where it's 10 feet to the first ground rod. Then we continue our conductor out another 3 to 10 feet, however far you want to go there, and drive the second ground rod. You could also put it down in a Y configuration. So you have the first 10 feet, and then you split it at that point to run to 2 ground rods in different directions. All of those work pretty well. My preference would be for the 2 ground rods, one on top of the other, if you're working in those sandy soils, especially I'm thinking down in the beach area. There is a table in both the ANSI standard and the ISA's best management practice that help you calculate your needs here, what your distances should be, what your depth should be for all of these configurations. And if you happen to be in a really rocky areas, maybe up in the mountains, you can use ground plates instead of ground rods. These are put in horizontally, so you have to dig a bigger hole, but it doesn't have to be as deep. So this can be less than 2 feet deep. The ground rods, or these ground plates, are typically 18 to 24 inches square. You need to run these at least 12 feet from the trunk. since they're not quite as efficient as the ground rod, we have to go out a little bit further. They tend to be a little bit more expensive than ground rods, but if you're driving ground rods into rock, this will greatly speed the process. So it will go much more quickly and certainly make up the price difference in labor savings. Now, I was talking a little bit about damage that we see around ground rods in our research plots in Charlotte. We have actually gone back in, pulled up ground rods, and then air spade excavated the roots around that ground rod, and we have measured this distance to roots that are injured. Again, we rarely see damage between the ground rod and the trunk, but we do see damage around the ground rod, and that is typically in a radius of 15 to 16 inches. So that's sort of our root killing zone, which is one of the reasons that we don't put ground rods closer to the trunk. Now, in some rare cases, if you're dealing with walks or driveways around the trunk and that's your only option, you can install the ground rod closer to the trunk, but you do need to let the client know that there is a downside of having it close like that, and that is that some roots may be damaged if the tree were to get struck. Okay, so we connect the ground rod to the conductor. There is a special purpose clamp for that. Now, the typical ground rod clamp that you can buy at Lowe's or Home Depot has a single bolt to attach it. The lightning protection clamps, again, specially built, they have two bolts that are used to attach the conductor to the ground rod. Note that the conductor here is on the outside of the ground rod. So as we tighten these bolts, we're tightening into the ground rod and squeezing that conductor from the back side. In the United States, it doesn't really matter if this conductor comes in from the top or comes in from the bottom. Most people put it in from the top. In Canada, it actually is restricted that you have to put it into the top. You know, this ground rod is not fully driven at this point. So after this is connected, we are going to get the back side of the ground rod driver or a sledgehammer out and drive this the rest of the way down. It needs to be at least a foot deep in the soil. So we'll do this connection closer to the surface. You can see we're just a few inches under the surface here. After it's tight, we'll then drive it down so that the top of the ground rod is at least a foot below the surface. And just an illustration here showing the depth of the trench, now only 8 inches, 10 feet out. And usually we dig a larger receiving pit where we have room to do our connection. We want to map that system, measure it out, and keep a record of that. So if there are any problems with it, or if the client wants to install irrigation in their yard, we can tell them where our conductor is and where our ground rod is so they can avoid trenching through our ground rod. Also want to point out another pro tip here on installing conductors. Notice this section of turf right here. It's about 8 inches wide, 8 inches deep, maybe 2 feet long in this direction. And when these guys cut this piece of turf, they only cut it on 3 sides. So over to the right here, that has not been cut. So instead of taking this whole piece out, what they have done is they've opened it like a book. They just flop it over. They may have to go a little bit deeper to achieve that 8 inches here to put the conductor in. But after they get this conductor attached to the ground rod, they'll simply flip this sod back over. And if the client irrigates, in a few weeks in the summer, you'll never even be able to see where that ground conductor is buried. So here are some of the pieces of hardware that we use. A section of ground rod that should be at least a 1/2 inch in diameter, the blunt tip, the conductor. Again, if you've been around the industry for a while, conductors used to be about 1/2 inch in diameter. Through our research, we've been able to get the standards changed. So now we know that we only need about a 1/4 inch diameter conductor here. So that works out to be about 1/3 as much copper. So there's quite a bit of monetary savings. And what we found at our lab is that most lightning strikes will certainly be contained within that 1/4-inch conductor. There are some real severe strikes every now and then that can damage it, but we have never experienced that in our research. So here's the ground rod clamp, upper right. There are 2 different types of ground rod clamps. This is for a single ground rod. This crossover type clamp here, it has a number 119 on it, has one direction for the ground rod and the other direction is for the conductor. So you can run the conductor straight through that ground rod clamp and attach it to a ground rod and run to the next ground rod without cutting the conductor. Now, most of these crossover clamps are made for that 1/2 inch in diameter conductor. We typically take a few inches off the end of the conductor and put it inside of this clamp to take up that extra space. We do want it to be secured to the ground rod. We have our drive fastener here. There are other fasteners available. There's one that comes to us from England that is a screw type fastener that you can extend as the tree grows. With our standard drive fastener, you need to replace that as the tree envelops the drive fastener. Down below, this is that ground rod compression fitting to turn 2 8-foot ground rods into a 16-foot ground rod on our sandy soils. And then we have numerous types of connectors. This is a side-by-side connector, so this holds 2 sections or the ends of 2 pieces of this 1/4-inch conductor. We find that this one is a little bit problematic. It is very hard to bend these fingers over so that it holds the conductor very tightly. So the conductor does tend to fall out of these. And also electrically, if we ever see a problem, which is extremely rare, it tends to be with this type of side-by-side connector for the conductor. This next one is an end-to-end. It's a pipe type connector. It has 4 screws. So we put one end of the conductor in one side and the other in the other side and fasten the 4 screws. A multi-purpose clamp, again, has many purposes. One is to connect 2 pieces of conductor together. So if we have to patch a conductor, or if we run out part of the way through the installation job, we would use that multi-purpose clamp. The other purpose for the multi-purpose clamp is to connect to a steel support cable. So if there are support cables in the tree or they're added later, that is the piece of hardware that you would use to connect the 2. And then the conductor down here at the bottom, we have spread the individual strands of wire apart just so you can see what it is made up of a little bit more clearly. So that is our lightning protection hardware. We also have some unique tools for lightning protection installation. We're going to need a hammer and pliers to drive the drive fasteners and then squeeze them around the conductor, or you can use this tool on the right-hand side here. This is a fence ply, and that has both capabilities of squeezing and driving. We blunt the end of our fence pliers so nobody gets that sharp end in the face. You also need a cable cutter. So these are for copper cables, so they're nowhere near as expensive as the steel cable cutters that you might use with support cable. And then a ratchet wrench, not illustrated here, but you can use a socket wrench or again a ratchet wrench. It makes it a little bit easier and quicker to do that underground connection with the ground rod. You're obviously going to need a shovel, a power drill, and an auger is really useful for drilling that pilot hole. If you're going to be digging deep, a tarp to collect that soil to make cleanup a little bit more easy. The ground rod driver, this is the more modern type of ground rod driver. On the right, you can see it has 2 handles. And actually, we've had them extend this middle pipe as well so that you're far less likely to pull that off the top of the ground rod. Now, some people use post drivers. They are not made nearly as well as a purpose-built ground rod driver. You can see that really big cylinder of solid steel up here. The problem with the T-post drivers is they've got this, it's fairly substantial steel, maybe a 1/4 inch thick, welded around the top. But after repeated use, what we see is those caps popping off. So if you're going to be doing this for more than just a few trees, it is well worth the investment in a ground rod driver, unless you have that demolition hammer that will greatly speed the process. This one is a little bit odd, the center drawing here. This is a spool holder, and it's really important for installing lightning protection because it prevents the conductor from kinking as it feeds out. Now, if we have a kink in the conductor on the trunk, it is much more likely that the lightning will jump out of the conductor at that point and go over into the tree. So we really need a smooth installation. And one of the easiest ways to ensure that is to have the spool holder that very smoothly feeds out your conductor to your climber who's pulling it up into the tree. So those are sort of the unique tools that you are going to need to have ready to go for a job. Now, in some cases, we're called on to install lightning protection at colleges or high schools or other places in the open that are open to the public, and we have to be concerned about vandalism. People trying to climb up a conductor, or they're trying to steal the copper. That one's a hard one to beat. But this is our standard vandalism protection system. Usually we just get some C conduit, the gray conduit, and we're really happy to have that gray color. It blends in a little bit better with the trunk. And we run the conductor through that conduit as we're installing it. So as it's going up the tree, we run it through the conduit. Usually this comes in 10-foot section and one 10-foot section with a sweep at the bottom of the tree. It is sufficient. It makes it that sweep makes it a little bit hard to pull out of the ground. And then we connect this to the tree. These are conduit hangers, and it's best if you can put a spacer below that conduit hanger to give room to grow so this doesn't become overgrown. It's going to be a little bit more difficult to adjust these as the tree overgrows. Next picture is a black flexible conduit, and this is fine as well. They tend to be a little bit more expensive than the PVC conduit. And again, they have their own unique fasteners. And you can see in this case where, again, they left some space for the tree to grow before it starts enveloping that conduit. Over on the right, you can see the conductor coming out of the top of that conduit. Okay, well, which trees shall we protect? Obviously, this is not an inexpensive service, so there are financial decisions that need to be made. So usually we look at putting these in moderate to high lightning areas, which is all of Georgia, but especially down in coastal areas, we're much more concerned. And we target, first of all, trees with trunks within 10 feet of a structure, especially a house, where the tree is taller than the house. And we do actually have a code on this that I'll come back to in just a minute. These aren't just randomly selected numbers. And then trees in recreational areas. Now, most public parks don't have the finances to do this. We wish they would. We think it would add to the safety of their users, but they don't. But where we do see this in recreation areas is especially on golf courses, and I'll come back to that. And then the high value and historic trees. Now, most people, if they were asked to do this list, would probably put it in the other order. Most people think of this as just a high value or historic tree service, but I like to think of it more of a somewhat protecting houses. Now, again, we can never sell this as truly protecting houses because we're not installing the system on the house, But if we're putting the lightning protection system into a tree that's right next to the house, it will most likely draw the lightning away from at least part of that house. So if you had a house surrounded by tall trees with lightning protection, that would do a better job. But again, even in that situation, we cannot sell it as protecting houses. There are people that do install house lightning protection, and they get to say that they protect the house. We do not. Okay. Okay, so this is where that recommendation for near houses comes from. It's interesting, it's from the National Fire Protection Association. And they call again for protecting trees with trunks within 10 feet of a structure when the branches extend above the structure to reduce that risk of side flash. So if we look at this situation, again, we have a tree that's probably 2 or 3 times, maybe 4 times higher than the house. But on this side of the house, you can see we have a steel cover over the chimney. We've got the electrical connection here. We can't see it, but there's an aluminum gutter over here. And those are all areas where the lightning may side flash to. So it's not unusual at all for us to see houses that are damaged, or they might even catch on fire, because the lightning comes down the tree and then jumps over to one of these conductive parts of the tree. And that again can ignite a fire in that house. So having this tree protected would be a really smart way to go. Another thing to think about when we're looking at protecting trees is trees have different susceptibility to lightning damage. So there have been surveys of which trees have evidence of lightning strikes. And that is this table that you'll find in the appendix of the A300 standard and in the best management practice, and show you which species we should be most concerned about. So in the South, we've got lots of species that we have to be concerned about. Probably our number one is tulip poplar. So if somebody has a tulip poplar near their house, they tend to get very large, very tall. That would be a prime candidate for lightning protection. Pines get hit fairly routinely, oaks. And then another sort of superstar for getting hit is a black locust. So typically we don't find those near houses, but sometimes we do. And again, those would be the ones, the high and the very high susceptibility species are the ones that if I had a choice, I would put the system in first. And that is, if we've got an oak and a tulip poplar next to each other, next to the house, I would go with the tulip poplar over the oak, unless one is taller than the other. But all things being equal, I would go with the species that are more susceptible to lightning damage. Then the recreation areas, especially where people may take refuge during a storm. Some parks actually have lightning shelters. They're just a regular shelter, like a picnic shelter, but they have a lightning protection system incorporated in them. And that's better than protecting people with tree lightning protection systems, but certainly the tree systems may tend to help. And then the golf courses. So after Lee Trevino got struck decades ago playing golf, most golf course superintendents take lightning protection very seriously. Many golf courses have every tree at a tee or green protected. Some have every single tree on the course protected. They also now have sensors for lightning that sound alarms when lightning is in the area, and that is also a very good thing to do to get people off the course, because again, we can never sell people lightning protection. All we can do is protect the trees. But again, most golf course superintendents are well aware of the risk of lightning and do take advantage of that knowledge and put lightning protection systems in. And then going back to the high value and historic trees, this one, Mount Vernon up in Virginia, tall tree, very close to the building, it would be a pretty obvious. Okay, so lightning protection systems are not once and done. We put them in and we've got to let the client know that they need to be maintained in the same way that a support cable would have to be maintained. So we would inspect them and we would do maintenance on the tree. So we need to let the client know that the system does need to be regularly inspected. The standard calls for periodic inspections. They don't really define periodic, but an annual inspection fits into most people's programs pretty well, and that would be a very justifiable inspection interval. So the client needs to be told that it's their responsibility to schedule that inspection. But that said, we as arborists should really be proactive about getting back to our clients on a regular basis. So annual inspection should be done as part of the routine evaluation of clients' properties would be very typical. So during the inspection, we'd want to look at the conductors. They can corrode, especially in the interface between the soil and the air. We often get corrosion there, especially in more coastal areas, sometimes underground. If we have a very acidic soil, it can eat away at that copper. So digging a little bit of the ground conductor up would be a good idea. Look for a tightness of that cable. Sometimes the kids will try to pull the conductor off or try climbing up it, and that can damage and kind of stretch that conductor out a little bit. So look for the tension and corrosion. Check the height of the air terminal. It may take binoculars to see it. You may not be able to see it when the tree is in leaf. And, occasionally we do get our drones out and inspect systems with drones. That can work pretty well as long as we don't have to get inside the canopy of the tree, but we can go up the outside on the side where the conductor is run and find out where that air terminal is located. And then we can look for signs that the yard has been trenched, things like, scars in the soil, disrupted turf, new irrigation system, are all hints that there may have been some trenching going on. I've been on sites that have been trenched for irrigation after the lightning protection system was installed, and a chain trencher just cuts right through that conductor and keeps it from reaching the ground rod. So much more likely to have problems in those cases. So look for those signs of soil disturbance. And when we're looking at those fasteners, kind of lucky for us, one part of the tree grows about twice as fast as the trunk of the tree. So if we look at the flares on the tree, it's a good indication of what's going on. So usually the first dry fasteners that get enveloped by the tree are the one or two that are on the root flare, which is nice because those are the easiest ones to see. And if those have been grown over, it's definitely time to look at the top of the system, because usually when the flare fasteners have been grown over, it's also time to extend the conductor at the top of the tree. So kind of a quick way, an easy way to assess that. What maintenance do we need to do? Replace the dry fasteners before they get overgrown. So if you can see it on this tree, like right in here, we've got a dry fastener that's right at the edge of being overgrown. So this is like a perfect time to refasten this system. So we would open up these fasteners. Typically they break when we open them. You use a screwdriver and a hammer sometimes to open those up. But we can free that conductor from the dry fastener, and then we'll install a new dry fastener right next to it. I'll show you that in just a second. So yeah, this is something we can do. Now this happens to be the old conductor, the 1/2-inch diameter conductor. The dry fasteners do come in two different diameters. So one for the 1/2-inch, one for the 1/4-inch. Be sure you get that correct when you're ordering your dry fasteners for maintenance purposes. Oh, so here's the new fastener installed right next to the old dry fastener. We do that so that there's no chance of flash occurring between the two. So if the new one is in contact with the old one, there shouldn't be any flashing going on. So this one is driven, but now we would come back, we would open this old one with the screwdriver inserted right here and twist it a little bit, and then take that conductor and put it in the new dry fastener. So we would also extend the conductor and the air terminal. Now, if we have the small conductor on the tree, we would want to go in with that same size conductor to extend it. We don't think that there's any problem extending the large diameter conductor, the half-inch conductor with quarter-inch, but it would probably be better to use the same material throughout. So if there is a half-inch conductor in the tree, then we'd probably want to extend at the top with more half-inch conductor. And then if there are any sections that have been enveloped by the tree or they have been cut, we can splice around those. Again, splices are opportunities for lightning to leave the system, so we would prefer to use the multi-purpose clamps because we can get them quite a bit tighter than we can get the finger type connectors. So here we have an overgrown conductor, and these should still continue to work as long as they aren't corroded within the tree. And from the outside, it's really hard to tell if they're corroded. So one thing that we can do is to really test a system that's partially overgrown like this. And to do this, we just need a hardware store type volt ohm meter. We will send a wire to the top of the system where a climber can fasten it into the conductor. And then at the lower end of the system, you can see it right here, we will clip in the other part of that volt ohm meter to the base of the tree, and we'll put it on either continuity check and listen for the beep, or look at the ohms. And the ohm readings should be pretty low, typically less than 10 ohms. If we have infinite ohms, there's definitely a break in the cable. If it's somewhere between 10 and infinite, there may be some corrosion going on within the tree, and it's probably time to replace a system like this that's partially grown over. And then we could also test the ground rod. Now, this one is not a simple thing to do. This one requires what's called a mega ohm meter or an earth tester. And this is about $1,000 test piece of equipment. It has two temporary ground rods and the wire that goes to the conductor or ground rod. So it's not something we would do on every system. But if you need to get that information and to test the ground rod, and you can also test new ground rods with this meter, there are standards on what they should read, and this is the meter that you use for it. Okay, well, what happens when the conductor is not repaired? So this is a case we often find. You can see here that the conductor has been damaged, and here's the end. So it's in the tree, but it was probably cut by a lawnmower and just hanging there. And this is actually what happens. You can see the hanging piece of the conductor here. So this tree was hit at least once by lightning, and that lightning went over into the tree and completed its route to ground through the tree, damaging both the lower trunk and the root that it went through. Okay, well, let's talk now about treating lightning-struck trees. So the treatment's going to depend on a lot of different things. How much damage is there? This tree, obviously, a total loss. Let's get the saw and get rid of it. But if it's less damage, we have to sort of judge the client's patience and their desire to keep the tree. But certainly not every lightning-struck tree needs to be removed. And, a guiding factor for many clients is their insurance policy. Many insurance policies will pay off on lightning-struck trees. The amount tends to be pretty low, typically like in the $500 to $1,000 range. So it's not a really big payoff, but it may push the client to decide one way or the other whether to keep it or to get rid of the tree. And then there may be other factors involved, sentimentality. I'm not sure of all those other ones, but there are other factors that go into the decision. So we're going to go through a series of trees that have been struck by lightning, and I'm going to talk about the treatment. And certainly if you want to contribute when I'm done, we should have some time for questions and discussion on these. So this one I would call minor damage. So what probably happened here is the lightning struck this tree. It was probably raining. The bark was wet. The lightning came down the trunk of the tree on the outside of the bark. And then for some reason that I can't necessarily explain, went into the tree at this point and blew off the bark. You can see the characteristic streak from that lightning strike right in the middle between the two edges of missing bark. So for this type of tree, we would usually retain the tree, treat, and monitor. But when you're there looking at it, you should look at the crown to see if there's damage. One thing that we can do, and I would especially recommend this in the spring and early summer, is to treat for wood boring insects or bark beetles and borers. At this point, if it is a high value tree, this damage will put out odors that insects can receive, and it may attract borers to the tree, and we could prevent damage by putting on that borer treatment if we can get there right away, meaning basically within a few days of the lightning strike. And then we'd want to put it on that annual checklist to monitor both the health of the tree and for decay progression. Now, it looks to me like the lightning did not do further damage to this tree, but quite honestly, you can never tell for sure. So having some patience here may pay off. Certainly I don't see reason to remove this, but there may be more root damage than we can see. And then the other treatment that we should recommend is irrigation during periods of drought. So if we have a summer drought that's more than a few weeks, putting irrigation on any lightning struck would be appropriate. And I'm not going to go through all these steps for each one of these, but that is one that goes to all of them, the insects and the irrigation. And again, if we have nutrient deficiency in the area, doing a soil analysis and fertilization may increase that growth rate, including the closure of the wound. And then routine pruning as with any tree. Now, this one has a little bit more damage to it. So I'm calling this one moderate damage, where the lightning did strike higher in the tree and then came down the trunk. So first off, again, we'd want to look for that branch damage. In this case, it did cause failure in a branch up top, and that is a broken hanging branch. So we would definitely want to get that out before it comes the rest of the way down. So we would want to prune out the dead and hanging branches, preventative borer treatments. And at that point, beyond irrigation, I think we would want to just hold on and see how things go. We're not really sure how much damage we have here. So waiting to see what's going to happen, meaning, at least until the next growing season, might be very appropriate before we put a lot of money into this tree. By the way, this tree was in the neighborhood I lived in Charlotte. And I followed it for years, and this lightning strike did not kill it, but the tree did blow over a few years later, like 5 or 7 years later, because of extensive root decay. Now, I cannot tell you for sure if that root decay was associated with this lightning damage or not, but in this single case, it was struck and there was root decay later on. So looking for root decay over time can be important in these trees. Now, this one I'm calling moderate to severe damage. It's actually a tulip poplar that was struck. And with one of these, you would want to discuss with the client that likelihood of mortality. And in many cases, the client may want to go ahead and remove the tree. Here's what the top looks like. And at the very least, we would want to cut back to non-scattered wood here, removing the dead branches. Now, I must say, any time that we are climbing lightning-struck trees, we have to be really careful. They can break under the load of climbers. Many climbers have been killed while trying to repair these trees. So taking preparations like binder straps to keep it from splitting, working from an aerial lift or a crane would be very appropriate. And then preventative borer treatments on a tree like this. And again, this one, if it had sentimental value, might be worth keeping, but you can see that the damage extends quite a ways down here. So we'd probably be taking off the top half of the tree, which if the client wanted that, you can certainly do that. But this tree and the amount of damage could go either way. And definitely we'd want to wait and see. This being a tulip poplar, we're going to be getting decay in there, but it may take 5 or 10 years before it gets. And then there are the easy calls, the shattered trees, the dead trees. It's this pine here, not the ones behind it. And this one kind of shattered at the top and lost all of its bark. But all of these, in my mind, are pretty easy calls for removal. I don't see any reason to consider keeping any of those trees. And then as we inspect over time the lightning damaged trees, we do want to look for those wood boring insects and decay. Now this is a tree at the Bartlett lab that did not have lightning protection system. It was struck. We know when it was struck because we look at all our trees pretty regularly. And this was 1 year after the strike, where you can see all these decay fruiting structures, and the decay has worked its way substantially into that tree. So the lightning will kill living cells, which makes it very hard to compartmentalize that decay. So with that, I'm going to wrap it up and just say that we have a couple of good references within the industry. First off is the A300 standard. We do have a lightning protection standard, and we also have the best management practice. I'm showing you the second edition of lightning protection, but we're actually on the third edition of lightning protection. You can buy these as a package through isa.arbor.com, or you can buy them individually. So with that, I'll end by saying that lightning protection is a very effective service. It's extremely rare that we see lightning damage to a tree that has a lightning protection system in it that was well installed and maintained. So it's extremely effective at preventing lightning damage. So with that, I'm almost to the end of my time, but I will stick around. And if you have any questions or comments, I would be happy to take them.
Thank you so much, Dr. Smiley. That was amazing. We do, of course, have a lot of questions.
Oh, 34. Yeah. Okay.
Yeah, we've whittled them down. So there's a lot in the chat, but also a bit in the Q&A. Before we hop onto that, I want to remind you all that your CEU sign-in sheet is dropped in the chat. So make sure you grab that link, fill it out. It's going to do a brief evaluation. And then once you hit submit, it will direct you to the CEU sign-in sheet to put in your credentials and get your CEUs. So make sure you do that before logging out today. And I'll stick around even after Dr. Smiley is gone, just to make sure you guys don't have any questions on that. All right. You guys want to get started?
Okay, yeah, I'll start with Dylan's question. How large are the explosions at the air terminal and ground rod? They're large enough in the air terminal to cause damage to the bark of adjacent tree parts. Usually they don't go beyond that. Usually they don't explode and break branches, but the bark damage may result in mortality. And as at the ground rod, we can see sections of soil being thrown a good distance, 10 or 20 feet. Typically those sections of soil are maybe 3 or 4 inches deep and maybe like a foot in diameter. It's not all the power of the lightning that's going into those. Usually it's the superheating of the moisture either in the bark or in the soil that explodes. Again, it's basically that steam that's produced that causes the damage. So next one from Guy, is the underside of a limb a better location for the conductor to keep it from falling debris and out of climbers' way? It certainly could. Most climbers tell me it's a little bit difficult to put it on the lower side of the branch. So they would, in general, prefer to put it off to the side. So again, they don't step on it, but it's still relatively accessible. Okay, from Teo, let's see. Have you ever researched lightning interact with full moon lights? Oh, powered through. So basically lighting systems, electrical lighting systems in trees are lightning protection systems. The catch is that they're ground to the electrical panel in the house. So they are not a particularly good lightning protection system, but it is not unusual at all for especially the 110 volt that is connected to the house panel to go over to the house. And since you brought that up, I will say that lightning protection systems are intended to protect the tree. They will reduce side flash, but it takes a lot less lightning charge to damage electronics within the house. So even in a lightning protected tree, we will not be protecting televisions and computers and video games inside the house. We wish we could, but we can't. If the client wants that sort of protection, they can have an electrician install a lightning, basically it's a fuse system within the house. And that is a better way to protect the electronics within the house. Guy again is asking, why is an inspection and treating of lightning damage included in the A300? I think that may be included in the appendix, or it has been included there. Is lightning damage primarily due to heat or the shock sound wave? I don't know for sure. I certainly know that the electricity doing that superheating is a very likely culprit there. The sound, I'm not sure of those theories. I better not comment on that one. Dylan, would you recommend bark application of fungicides in addition to borer protection for treatment? No, I would not. I don't see the value. The fungicides are not going to keep the decay fungi out. They're not persistent enough to do that. So in general, I would say no. I would just stick with the repellent type insecticides. Oh, Dave Leonard. Hey, Dave, why are certain trees hit more than others? Are they better grounded? I'm not really sure about this one. And I don't know if you caught it. I was saying they are more susceptible to harm. All the surveys of lightning struck trees that do go into those lists have to do with damage to the tree. So is a tulip poplar actually more susceptible than a beech tree? We think so, but we can only really judge it by the harm to the tree. We see a lot more damage on tulip poplars than we see on beech trees. So don't really know. Another one from Guide, would sounding be part of inspection if the bark is popped off? Should this be done along the streak of apparent damage? Yes, I think that would be very appropriate if you're doing that level 2 risk assessment on a lightning struck tree. Using a mallet sounding for decay, it usually is much worse near that streak of damage. So sounding would be very appropriate there. And lastly, from Carl Hall, has any research been done to assess plant growth regulators treatment to lightning damaged tree? Does it help? There's been one study that I know of that looked at plant growth regulators in association with wound closure. And if I recall correctly, it slows wound closure down. So in general, it's not something that I would recommend. We don't have full knowledge here. And sort of the converse of that is paclobutrazol, the common tree growth regulator, started its life as a fungicide. So there may be actually some fungicidal benefits. We do see that on foliar diseases to some degree, but I wouldn't really count on it from a wood decay perspective. So in general, I would not recommend plant growth regulators for lightning struck trees. With that, Brittany, I can turn it back to you.
Oh, there we go. Okay, awesome. Thank you so much for all of that. You did a wonderful job. I already see all the evaluations rolling in. Thank you guys for filling that out. Everybody has very much enjoyed it. So we appreciate you spending your evening with us and helping out the GAA tonight.
Thank you. Happy to do it. And best of luck to GAA. We're happy to see you as an upcoming chapter with the ISA. We hope that you'll get that to status soon.
Thank you. Thank you. Y'all have a great night, and I hope to see y'all at another event soon. Thanks.